Let's try and see if we can improve the thermal problems with the rectifier here on the 3 amp output. See, I drilled a hole as close as possible to the heatsink, and then I mounted it on the inside here, close to the heatsink, because the iron that this case is made of doesn't really transport heat as good as aluminium does. But if you put it very close to the heatsink, it's actually going to be okay. At least this is expected to be a million times better compared to this tiny little 0 gram thing that is inside a closed case. And also we're going to try and improve a little bit here. Here's what they have done. Let's look at the rectifier is here, and that will be the AC input. See, the negative side of the rectifier, that is correctly made. It goes to the capacitor, and then we take the power from the other side of the capacitor. That is the clean side. Well, let's look at the positive side. See, there's a thin track here. We got some other stuff going here. We got a trimmer, some resistors and stuff. And we also got a power supply here and stuff. And that means this is not really a good way to do it, because this track down here, that is the high current track. That is now infecting all the stuff here. What they should have done is they should have had a track going to the capacitor, and from the capacitor taken all the outputs, so the output is not sharing the peak currents to the capacitor. And that is why I solder the wire from my rectifier here. I will solder the cables here, and then I will put it here. So now it should be a lot better when it comes to ripple. Also, I'm going to change this sense resistor that we talked about in the previous clip. This is running insanely hot, and it is 0.15 ohms and 3 amps. Well, do I need to tell you more? Use Ohm's law to get a clue. Maybe the value can be lower, so that means we're gonna dissipate less heat. It depends a little bit on the pot meters here and stuff, so that is what I'm gonna experiment with first. So that was a lot better with the rectifier here. I should maybe put some heat grease under the rectifier to get a little bit better thermal connection, because I can feel the metal here is really not getting warm. And let's see what happened to the rectifier. So it's 80, 90, and it has been running for a little while now, 90 Celsius, but that is still a lot colder compared to before. So that has improved. I've been running this for a little while. So, well, let's see this resistor. What it is, a 170 Celsius. That is a way too hot for a resistor, especially when its properties changes that much with the temperature. So this is the rectifier. It's called CP602. It handles 3 amps at 25 Celsius. And let's look at the derating curve. So this is the temperature, and this is a PC board mounting that it was actually mounted. And here's a metal heatsink, or if it's screwed onto a big heavy duty metal heatsink. And so 100 Celsius you can handle now 4 amps. So that is the improvement that I have now. And in the good old days, well, 3 amps, no. Let's try and go all the way mega sized a rectifier for 3 amps. But anyway, that helped. Look at the temperature now, it's amazing. Size does matter. of course this will have a lot better thermal properties because it is that big, and I didn't even put thermal grease underneath it. That's the way to do it, and there's plenty of space to do it right. So I'm trying to rework this a little bit so we can make a 4-point current measurement, so it should be more stable. This is the ultra hot current sense resistor, and this is the ground return from the output terminal going back to the capacitor. So it's actually done quite all right here. The 3 important sense points, they're very close to this point, so it's kind of all right. I would have put them all 3 in one side and then current in the other side. But look at this long track. So all the 3 amps, they go this way, but here and here and here. So all this copper, when all this copper is heated up, it shares a path with the current readout. And copper changes a resistance with temperature a lot, actually. It is really not supposed to be used as a part of the sense resistor or measurement system at all. So that is also a big problem. So we're going to take the current points to one side of a resistor, and all the voltage stuff that is relevant for sensing also on the resistor, but closer. So we're going to see if we can make a Kelvin style system for the current readout. I take the 2 points for the current path. That point is where the thick wire goes, and this point is my ground return. So that is my power wires to my resistor, and now I can take 2 wires here and put to my resistor as the sense wire. So now there's no current flowing in anything here, and I will have the same voltage on all points here and the same applied to all points here, and it's not going to be affected by temperature changes in any solderings or any copper or anything like that here. All I have to do is solder another wire here and here. I am not giving up that easy about the current readout. Oh man, I was about to blow my own little fuse last night. Of course I fixed all the current measurements here and everything is now perfectly fine. I run on ice cold resistors and 4-point measurements, and it's rock steady. When I measure the voltages here, it's super linear, and wow, now we're talking about some current measurements that can be good. So that goes up to this board that is the meter selector, and you would of course expect voltage and current from the other one here to go in a balanced form via this switch. Again, go out to the meters, and then super duper, we're done and deal, right? And of course the 4th section of the switch will just be driving the 3 LEDs, and as you see here, the LEDs, they are just mounted in series, easy. There's a common blue. But now comes the funny thing. If you remove the connector to the LEDs, and that's all it does, driving those LEDs, right? Now this meter is not working at all in anything. This meter is dead. Voltmeter here works fine. This meter is dead. So the LEDs driving has something to do with that meter. So I thought, what the heck is wrong? This can't be right. Now you're gonna see something funny. This is not a resistor system. No, it's an optocoupler, 4-way optocoupler, and it is fucking around. Excuse my language, but this is totally wrong designed. And they're sharing some of the signals for the LED. Of course, they're using the constant 5 volt for the 5 volt meter to drive the LEDs, and that's perfectly fine. You could have done that, but that should have been done with a separate wire that has nothing, that is not sharing with the voltages and stuff like that, but it's involving the current readout and optocouplers for voltmeters stuff. It's not linear at all, and it's never gonna work at all. That is as wrong as it possibly can be. So I have to remove this chip and put in resistors instead and reroute the LEDs so it's gonna work. And it's, what have they done? No, I'm getting frustrated because I've never seen anybody do something as wrong as this. Yeah. So here's this bad boy out. Oh man, I can see that there's a black wire on each side. They're all configured the same way with the colors and all that. So what I'm doing here is I'm adding a little dot for black wire identification, and those are the meters. That will be the LEDs, and that will be the 3 different power supplies. They're all configured the same way. So it's black and yellow, that will be current, and blue and red, that will be voltage. So now we just need to reroute everything so it's correctly done and figure out exactly what is the funky trick with this optocoupler thing, the K847P. So that is definitely an optocoupler, but that is not going to be here anymore. And also I need to figure out how to drive the LEDs. I just have to one resistor and a separate wire to and back going to the 5 volt here. Separate wires, so they are not sharing the different currents you will have, or the different whatever is gonna happen when you switch. Of course you can't share this with critical readout wires. So optocoupler removed. I thought I could just poke around with the way that everything here is connected. Is the way that they made the LEDs connect to everything, and the way that this is not going to work at all. But what I did is I tried to connect the black and the yellow from 5 volt 3 amp output, or this is the current sense. So it's just connected directly to the black and the yellow, the amp meter, just to prove that everything is right. Okay, so this is 0 amp, 1 amp. All right, let's try and see if we change this to 2 amps, 3 amps, 2 amps. I will bet no one else with this model power supply have ever seen this amp meter go as accurate as I just showed you guys. So that is the trick, is remove this, remove the optocoupler and connect everything here without this crap that is not working. Then it's gonna work. Of course I tried to connect the voltages over, and the voltmeter works fairly okay. Let me explain exactly what they've done, because this, where is it? This switch, as you see here in the middle, it is 4 sections, 4 individually isolated sections with 3 positions. So it's drawn like this. So that means this is in the left position, in the middle position, they all switch to the middle, and so forth, right? So this meter is, that means the left position is A and B volts. So that means voltage 1 and voltage 2, or voltage A and B, right? It goes to the 2 meters like this. So in the next position we got current and current. So it's again just current and current going in like this, balanced, and so forth, right? But we also got the LEDs. So we actually needed a 5-section switch, and it doesn't exist in this tiny little size they wanted. It's also much more complicated, and it's bigger and it's more expensive. So the idea is that all of these are balanced and also isolated between all the different outputs, because you can parallel them or serial them or whatever you want. And of course it should be like that. So by taking an optocoupler and driving the ground sides of the volts or the currents or whatever you're doing, should not be affecting the readouts in series with the LEDs, you get the possibility to switch the voltages or the currents with the optocouplers, and this way, this is of course a fully isolated product, because it's for individual optocouplers and diodes and all that, right? And this way, it should be possible to make this work with a 4-section switch. However, driving optocouplers and also the way that they switch, it's not perfect. You require current to switch them, and also they don't switch completely on or completely off. So this is a perfect way to screw up the readouts, as I've shown you guys. Amp meter is just absolutely bad, and that is because of this optocoupler solution. So the only way to fix this is to get a proper 5-section switch and do it the right way. Whew, that took a little while, but now this nice power supply is fixed. Okay, we don't have those LEDs anymore, but who cares really? As long as I get accurate metering, that is what I want. Then I can use it. So all this crap with the optocoupler, that is gone, and we're directly connected to everything here. There was a yellow wire we don't need. That is the voltages driving the optocouplers and some stuff that is not needed, of course. And yeah, did I show you guys the new sense resistor system for the 5V 3 amp? And it's been running for like 10 minutes now. And let's have a little look. Ooh, 44 Celsius. So that is really working good. I was expecting a little bit more even distributed temperature. I think this one is a little bit better cooled, because it's glued on 2 sides. Also the rectifier is running nice and cold, like 57. So that is great. There's nothing else on this PCB that gets hot in any way. It's really, really nice and good, this PCB, when it comes to everything else, really. Also, what I found out about the other power supplies, the top trimmer here, that is the voltage readout, and the trimmer down here, that is the current readout. The one further down here, that is the maximum current. That means when this knob here is all the way to the right, then how much is maximum? That is adjustable by that part. So I just set this to 2.1 so that I always get at least 2 no matter what. There was another problem with the volt knobs. Of course, I have said this before, and that was the unconnected pin. That is, of course, not how you do this. So you, of course, always connect the 2 left pins like this. And there was another problem. This one went all the way to 40 volts, and this one went to 35 volts. So I added a maximum voltage setting resistor. So now it's 31 on each of them. So that means, of course, I can get by 30 and then a little bit more. And that's perfectly fine. This is exactly what I want. So yeah, all I need to do is now assemble it and be happy. Just to find out if it's me who's a crazy fool, or is lying, or there was something specially wrong with the unit I had before. Maybe it was a prototype or something was defect or whatever. I just went and picked up another one of this model LR2302. So let's try and see about the amp meter. This is in C, and this one is all the way to 3. let's hold this one in the middle, and I did not touch anything, of course. So we are in on. That was 1 amp. And I mean, this is 1 amp plus minus 1 milliamp. That is 2 amps. Oh, that's actually fairly accurate. And 3 amp is way too much. So, okay, 2 amps, 1 amp. It's only 10% low here. So this one is not that bad, actually. Let's see if we run a little bit. So this is a little bit 890 maybe. Let's just say 900, should we? Okay, 2 is super accurate. So this is exactly the point where they trimmed it. And 3 is way too much. It looks like. Yips, see? It actually goes to, whoop, current limit. Okay, so let me give it 3 amps, but it's still, yes it is. It is pulling 3 amps. So let me try and dial in. Should we do that? We should be able to do that, yes? Good. So here we go. That is our 3 amps. Spot on, isn't it? So let's dial this down to 2 amps is, ooh, okay. And let's see about the 1 amp. That is actually, this meter is actually a lot better. But it's still not good, is it? See? So definitely what you do is trim this for the range where you want to use it, and then live with too much and too little on each side. That is just how it is. Yeah. Otherwise, you can do this mod that I explained about previously in the video about removing this optocoupler, and this is, of course, they need those diodes. But it's quite sexy with the LEDs, I must say. Or can you find a 5-section switch? Then you can do all of it in one go. So this is the 2 amp output, and again we're attacking the right meter. So this is 1 amp. This is how it was originally. And this is 2 amps. So 2 amps a little bit too much, 1 amp a little bit too little, right? So this is as good as it can be. Here comes the fun thing. Let's look at the left power supply, which is not going through the optocouplers. See, this is 1 amp. This is 2 amps. Haha. So, when you're playing with something and you want it to be accurate, when it comes to amps and volts and whatnot, the left meter here is by far the best one. Just use this power supply for accurate things, and then you don't need to do the mod. If you can live with that,